Let's talk about sulfonation. Let's say we have a benzene ring and we're adding fuming sulfuric acid, and we'll form this product which looks like this. Now this is an electrophilic aromatic substitution reaction, so we need an electrophile that will be attached to our benzene ring. So in this case our electrophile would be sulfur trioxide. But if you look at the structure of sulfur trioxide, which looks like this, you'll probably think, okay, this compound is neutral and it does not have any positive charge, which might not be a strong electrophile, but I say that sulfur trioxide would be our electrophile. Now, you know, we're adding this fuming sulfuric acid, or let's say sulfuric acid is constantly in equilibrium with sulfur trioxide and water. So if you add more sulfur trioxide, you'll form fuming sulfuric acid. And in the lab, when you see that, okay, something is written fuming sulfuric acid on a container or something, that means that the reagent is sulfur trioxide. And you can shift the equilibrium by adding more sulfur trioxide to form fuming sulfuric acid. Now, as I said, this is our structure for sulfur trioxide. And you can also imagine something like this, that all the double bonds between sulfur and oxygen, let's say that these double bonds are breaking and the electrons are moving towards this, you know, oxygen atoms. And you can imagine that these single bonds between sulfur and oxygen right now, and these negative charges due to the lone pair, due to the extra lone pair of electron that is adding to that oxygen atoms. Now we have 3 negative charges, and you can see that, okay, we have a +3 here for the central sulfur atom. And now, even though this compound is neutral, this sulfur atom is very, very electron poor. Since this is very electron poor, this can act as our electrophile, and the benzene ring, being electron rich, would be our nucleophile. Now let's talk about the mechanism. Right? So let's say we have this sulfur trioxide, and we have our benzene ring here, and one of the double bonds will attack the central sulfur atom because this is electron poor, and the double bond between sulfur and oxygen will shift on to this oxygen atom, right? So we'll form an intermediate. This oxygen atom has a negative charge on it, and we had double bond here within this benzene ring, but the double bond between this carbon and this carbon is broken right now, so this carbon has a positive charge, as this carbon is already attached to a sulfur atom. And if you look carefully, you'll see that, okay, we also have a hydrogen here connected to this particular carbon atom, right? And this structure can also be in resonance with two other structures where the double bonds within the ring will move around to compensate the positive charge, and which will look like this. I'll just show you. So the resonance structure would be something like this. So this double bond will try to move there. So now we have a positive charge here, but we have a double bond here, and we have a double bond here. We have a hydrogen here, and we're connected to this sulfur trioxide with a negative charge on one of the oxygen atoms. And the next one would be this double bond will try to move here. I mean, the electrons from this double bond will try to move there to compensate the positive charge, and we'll have a positive charge here, and we have a double bond here, double bond here. There is a hydrogen here, and we're connected to our sulfur trioxide. And this is called sigma complex. Right. So this is our first step. We form an intermediate, right? In the second step, we will try to remove the hydrogen. We'll try to remove this hydrogen so that we can reform our double bond here. And for this, we have water when we're using this sulfuric acid, right? Because sulfuric acid always in an aqueous solution. So that means, let's say we have this intermediate here, and we have double bond here and here, double bonds here and here, and we have our water. We have lone pairs of electrons on this oxygen atom, and this will try to pull off this hydrogen atom. The bond between this carbon and hydrogen will break. The electrons will be left into the ring to form the double bond. Now we are reforming our benzene ring like this, and now we are only left with our sulfur trioxide. But as you can see, we have already a negative charge on this oxygen atom, right? We have a negative charge here. So there is an additional step in contrast to our other electrophilic aromatic substitution reaction, like nitration or Friedel-Crafts alkylation or acylation. So in the next step, you know that the sulfuric acid usually can stay as H2O plus, and as well HSO4 minus. So in this particular case, since we have this H2O plus, that means let me draw the structure. So we have these H3O plus, there is a positive charge on this oxygen atom. So that means this negative charge, so this will try to pull away this hydrogen, and the bond between this oxygen and hydrogen will break. The electrons will be left on this positively charged oxygen atom, and we will form our final product that looks like this. And also maybe water here, or you can also write this like this. So this is the mechanism of sulfonation reaction.